What would you do if I asked you to add up all these numbers? Or what about these ones? Well, I can imagine either you'd spend a few hours in significant pain, or you would punch me, which, hey, I get it, that's a fair answer. But what if I told you that adding stuff like this up isn't nearly as hard as it looks, and there's actually a pretty easy way to go about this? So let's talk about it. So those little fellas are called sequences, which are basically ordered lists of numbers. Now we denote them with a letter, usually A, and a subscript. So for example, A sub 1 would represent the first term of your sequence, A sub 2 the second, and so on. Now usually these numbers have some sort of pattern, but sometimes they don't, and they can also be finite or infinite. So basically sequences can be whatever they want to be. Now what you actually saw a few seconds ago are called series. Now these are the same thing as sequences, but instead of commas, they have those dreadful plus signs. Now we denote these usually with a capital S and a subscript that tells us how many terms we're summing. So if you're summing the first 10 terms of a sequence, for example, you'd call that S sub 10. So with that in mind, let's look at the two most important types of sequences that pop up a lot. The first of which is the arithmetic sequence. Now this is a sequence where each term is a common difference d more than the term that came before it. So let's look at a quick example. Like the positive integers. Each positive integer is one more than the positive integer that came before. So this is an arithmetic sequence. So we can define these by our initial term, which we'll call a sub 1, and our common difference d. If we were to write out a generalized form for an arithmetic sequence, it would look something like this. And as you probably are starting to see, if we were to find the nth term of an arithmetic sequence, we could always write it as a sub 1 plus n minus 1 d's. Now, the reason why it's not n times d is because remember that first term doesn't have any d's, so it throws the whole thing off by 1. A good thing to note is that these numbers don't have to be integers. In fact, they can be any real numbers. So for example, this right here, maybe not as pretty, but still an arithmetic sequence. So now let's look at what happens when you try to sum these puppies up. The best way to understand this is probably through the workings of German mathematician Karl Gauss. Now, when this kid was in like 3rd grade, his teacher asked him to add up all the numbers from 1 to 100. And what he saw was kind of crazy. He took the first term 1 and the last term 100. He added them up to get 101. Then he moved one step inward, did the same thing with 2 and 99. He also got 101. Same thing with 3 and 98. 4 and 97. So what he found is that you can take an arithmetic series and break it up into a bunch of pairs of the same sum. So with that information known, we can pretty easily write a sum for any arithmetic series, right? We take the sum of the first and last terms and we multiply by the number of pairs of that sum, which is simply the number of terms n divided by 2. Amazing. So in this example, you take the sum of the first and last terms, which is 1 plus 100, you're going to get 101, and you multiply that by the number of pairs, which is simply 100 numbers over 2, 50 pairs. So multiply those two together, you're going to get 5,050, which should look familiar. That is indeed the sum of the first 100 numbers. So arithmetic sequences and series, easy peasy. Let's move on to the next one, which is geometric. Now, in a geometric sequence, very similar to an arithmetic sequence, except instead of adding a d to get to each following term, you're going to multiply it by a common ratio, r. So we can write each term as the term that came before it times r. And I forgot to mention this earlier, but this is what we call a recursive definition, because the definition for each term depends on a term that came before. A good example of this would be like the positive powers of 2. To get to each following term, you're multiplying by another 2, right? So this has a common ratio, meaning it's a geometric sequence. Now, if we were to write a generalized form for this type of sequence, it would look pretty similar to the arithmetic type, except instead of adding d's, you're multiplying by r's. So instead of having coefficients on that d, you're going to have exponents on that r. And for the same reasons as before, the nth term of a geometric sequence is always going to be a sub 1 times r to the n minus 1 power. Not too bad, right? So now let's look at what happens when you try to sum these numbers up. Unfortunately, there's no simple genius way to do this like there is for arithmetic series. You can write out a generalized form and factor out an a sub 1, but you're going to be left with this, which makes me sad because I have no clue what to do with that. So with stuff like this, we have to get a little creative. Usually with series like this and in a lot of other series, we want to try to write stuff in a way that'll allow us to cancel out terms. So what would happen if we took our initial series and multiply that series by r? Well, we're just going to raise the exponent 1 on every r, right? But here's where things get interesting. If we subtract these two, all those middle terms are going to cancel out, and you're only going to be left with a sub 1 minus a sub 1 times r to the n. So if we factor out that s sub n, we can actually find a pretty easy formula for the sum of any geometric series. Your initial term a sub 1 times 1 minus r to the n over 1 minus r. That's it. So the last thing we're going to do is talk about those horrible examples that I showed you earlier. Let's start with the first one. So the first step in any problem like this is always diagnosing the series. We can notice that each term is 40 less than the term that comes before. So we can safely say that this is indeed an arithmetic series. And another thing to note is there is a big dot 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 thingy in the middle of this. So it isn't just 5 terms. It's probably tens, hundreds, thousands of terms. And we don't know that yet. But this should be pretty easy with our handy dandy formula, right? We just take the sum of the first and last terms, you multiply by n over 2, and we're done. Well, we can easily find the sum of the first and last terms. We just gotta add them up, and we're gonna get 413,204. Big number, I know. Now the tricky part comes in finding n, because they don't tell us how many terms we have here, and there's not a super easy way to kind of just know. But if you remember, we can always write the last term of the sequence, which we'll call a sub n, as a sub 1 plus n minus 1 times d. Well, we already know a sub 1 and a sub n, and we know d now, which is negative 40. So with that logic, we can find n. If we do a little rearranging, we can find that n minus 1 times positive 40 is equal to 159,960. Now, I do not want to divide that number by 40, but that number looks awfully close to 160,000, which I know is 4,000 times 40. In fact, it's only 40 less than that number. So that big number is 3,999 times 40, meaning that n minus 1 is simply 3,999, making n 4,000 terms. So now we have everything we need. We can take that big sum that we found earlier and multiply it by 4,000 over 2, which is 2,000, and we're going to get that big number, which I am not going to say, but you get the point. Pretty cool, right? So the second example is actually somewhat easier, believe it or not, although it looks like hell, but it's gonna be fun. First step, always diagnose the series. Each term, we're doing a few things, but one of those things is dividing by 8, right? You see those increasing powers of 8 in the denominator. That is one sure tail sign to know that this is a geometric series. But we're also multiplying the numerator by something, which is negative 7. So that means that our common ratio is negative 7 over 8. Now the next thing to notice is that this is actually one of those infinite series that I was telling you about earlier. Notice we don't have an ending point in this series, it kind of just goes on forever. So that may be a problem, but let's write down our formula and see what we can do. Remember, the sum of any geometric series is your initial term times 1 minus r to the n over 1 minus r. We don't have an n to use because this goes on forever. So the first thing we have to do is assume that the absolute value of our common ratio is less than 1. Now, if it was 1 or more, the graph of our sequence would kind of skyrocket to infinity, and that means our sum would also be infinite. When our absolute value of our ratio is less than 1, it asymptotically approaches 0, which is what we want, right? We want a value where at some point you're not adding anymore, you kind of just settle in at a certain sum. So that's the first thing we have to assume. With that assumption, let's think about r to the n. What happens as n goes to infinity? Assuming that the absolute value of r is less than 1, that means that r to the n is going to approach 0, right? If you're taking a number whose absolute value is less than 1 and multiplying it by itself an insane number of times, you're going to get a really small number, which is eventually going to approach 0, which means that 1 minus r to the n is going to approach 1. So we can rewrite our formula like this. The sum of an infinite series is our initial term over 1 minus r. We know our initial term, which is 45, and 1 minus r is 1 minus negative 7 over 8, which means that we're dividing 45 by 15 over 8, which means our answer to this crazy expression is simply 24.